Thank you very much for joining. My name is Udbhav. I'm a second-year undergraduate student at McMaster University, and today I'll be presenting my research on abdominal organs auto-segmentation to reduce patient wait times in radiation oncology treatment starts. I also want to acknowledge that UAB is on the traditional lands of the Muskogee Creek Indians. So before we dive into exactly what our research is, it's important to understand what the current workflow is for someone who needs to receive radiation. Of course, the first step is the patient is recommended for radiation. This usually happens by a board of MDs and medical physicists who get together and they decide that, yes, this person would likely benefit from radiation therapy as opposed to any other therapy. In the second stage, the patient undergoes a CT scan for planning. Now this helps us, and you'll see why, but specifically it helps us to identify their interior organ structures. You may be asking, well, don't we all have the same organs? Why do we have to take a CT scan for every single patient? Well, we do, but every person's organ structures are different and slightly different ways. So in order to have the maximum precision for every single patient, it's important to have a CT scan. Now using the CT scan, a radiation oncologist will go through and identify organs of interest and our target volumes. Target volumes are something that we want to irradiate very intensely, and our organs at risk are anything around around our target volume that we do not want to irradiate. Using these segmentations, we're able to complete a radiation planning. And finally, the patient is ready to receive radiation. Now, in developed countries, and depending on manpower and time efficiency, this takes anywhere from 1 to 3 weeks. Now, this is a significant amount of time. And what we've identified and what we propose is to use a deep learning model in order to identify our organs at risk and our target volumes, and having those plans be submitted and verified by an MD. Now this takes our planned turnaround time from 1 to 3 weeks to 1 to 3 hours. This is a significant reduction in time. Now it's important to understand exactly what contouring is. So when we talk about contouring art, typically we talk about making an outline around something or identifying where something is in the picture. In this case, what we can see is a CT image taken directly from our dataset. Now for the untrained eye, it looks like a series of organs and bones and other things that we can't really tell what it is. So what a medical physicist and a radiation oncologist will come together and do is identify a list of organs that they want to identify in each and every single slice of the image. Now as you can see here, this ranges from the spleens to the kidneys and livers and stomach and so on. And what we can do is, using these segmentations, stack them one on top of the other, because a CT scan is of course three-dimensional, stacking them together to perform or to identify a 3D organ structure for every single patient we look at. Once again, this allows us to identify the organs at risk, so where we don't want the radiation, and our target volumes, where we want the maximum radiation. For example, we can see in our list that an organ that we are interested in is a spleen. We can see it here on the 2D image, segmented. And finally, we can see stacked across all of these different slices of the CT image, the 3D version. We can do the same for any number of organs, in this case the liver and the right kidney. Now the question is, how does this actually affect how they get radiation? These are just pictures, these are just colors. Well, as we can see here, this is something similar to what we would see in a radiation planning session. So in this case, we can see the linear accelerator, or the LINAC, at various configurations around the patient's body. And we can see that there are various organs identified here, just as you could see in the previous slide. Now what we can also see is that we're identifying areas of high radiation in red and low radiation in blue. Now, I think an interesting case here is where we can see the rectum identified in orange, which is directly in front of our target volume. So we want to irradiate our target volume in dark red with as much radiation as possible without hitting the rectum, so we don't cause any other sicknesses. And as we can see, the radiation planning software is able to accurately identify that they need less radiation in the middle and higher radiation on the edges. And this is just one case where we can see the modularity of the radiation planning process. All of this to say, these pictures help us optimize our dose deposition during the treatment planning process. Now, the way that we're able to do this is using a deep learning model. And when we're using deep learning, it's important to understand exactly what data we use. In this case, we're utilizing the AMOS22 dataset, the Abdominal Multi-Organ Segmentation dataset, which consists of 500 CT and 100 MRI image label pairs. Now, sample image might look something like this, and its corresponding label might look something like this. Now, the most important thing to note is that these are not auto-generated. So these are generated by someone who's trained and experienced, and they've done this for 600 patients. Now using this data, which once again is 600 images, we split this up into 300 images for our first stage of training. And further, we split that up into 200 images for training and 100 for validation. Now, the reason we have a split like this is fairly common in deep learning and machine learning practices to have something like this. Now what we do with this data is we pipe it through a custom UNet-R framework. And you may have heard of the UNet framework, which is fairly standard for medical image segmentation. But in this case, we found that a UNet-R framework allows us to deal with a linearized projection of our 3D flattened patches in the very final layer using transformers, which are quite common in natural language processing. Now, we ran all of this training on the Jetstream 2 high-performance compute cluster for around 185,000 epochs, and we validated every 500 epochs. Now, before we jump into exactly how we were able to assess our model's accuracy, it's important to understand what we mean by assessing our prediction accuracy. What we use is something very common, state-of-the-art, in image segmentation. This is called the dice similarity coefficient, and mathematically it can be represented like this. However, I find it much more useful to look at a pictorial representation. In this case, imagine that we have our predictions, so our model predictions in red, and our ground truth, or what our medical doctor will tell us, in blue. In this case, we can see that our predictions are very much removed from what the doctor tells us. There is no overlap, so our DSC is 0. It's quite bad for us. We can see in this case that there's some partial overlap, so we agree in some parts and we don't agree in others. And in this case, our DSC is anywhere between 0 and 1. Finally, we have a picture-perfect, pixel-for-pixel agreement between our model and what the NB tells us, and this is a DSC of 1. Now, keeping all of this in mind, we can look at our model results. As we can see here, across all of our regions of interest, we have fairly high dice similarity scores. And in fact, we were able to achieve an average dice similarity coefficient of, across 7 validation images, of 0.849. Now this is fairly high, and we see quite a large degree of agreement across all of our regions of interest. However, we do notice that there are some outliers, in this case specifically the prostate and uterus. Now, while we don't exactly know why this is the case, we're currently investigating, but what we suspect is poor annotations in the dataset, or even other factors that we haven't yet identified. Now, further investigation will likely be increasing the number of training epochs, because we know that this will help. Now, the way we know this is because we can see on this graph here the loss, which goes down over time, which is what we expect, and the accuracy, or the dice similarity coefficient, which goes up over time. And we've reached our best DSC at an iteration of 165,500, if you remember, out of 185,000 total epochs. So because we reached our DSC fairly late in our training, we know that there's likely a lot of room for improvement if we simply increase the number of training intervals. What we also want to implement is a human-in-loop testing strategy, wherein we pass our model predictions along to an NB, and we ask them for their feedback on exactly what would need to be changed to make this clinically viable. In addition, we want to include hyperparameter optimization and k-fold cross-validation in an iterative process, as well as comparisons with existing frameworks, such as the Auto-3D-Seg by MonAI, the Medical Open Network for Artificial Intelligence, and NNUnit by Eisen et al. By benchmarking our results against theirs, we'll be able to understand exactly where we fit in the larger picture. In summary, we know that manual segmentation takes a lot of time and effort. We can understand that CT images are crucial in planning. We understand that these segmentations help us to deliver optimized dose depositions. And in order to achieve these results, we've used the AMOS22 dataset. We've developed deep learning pipelines to leverage this dataset for auto-contouring purposes. And we've implemented this framework successfully, and we're currently assessing results. With that, I'd like to thank all of my contributors, Dr. Jeffrey Peacock and Dr. Carlos Godinez from the University of Alabama at Birmingham, and the Jetstream 2 high-performance compute cluster. Thank you very much. Yes?
Can you go back to the slide where you were talking about like training and stuff? Yeah. So, bear with me, because I don't really know machine learning, but what I'm curious about is every time you do this kind of procedure, would you show it the computer the same 300 or 200 images for training, or would you show it a new set of 200 every time?
Right. So pretty much the way it works, I guess with machine learning in general, is we have training images and we have validation images. So what we're able to do is we're showing it the picture without any labels, and we're showing it the labels. And we say, tune whatever parameters you have to get from A to B. And And what we do is every 500 epochs, we have a validation image. So we have a random image that it hasn't seen, and we say, okay, well, using this image, which you don't have the labels for, try and generate the labels. And then we compare that to the existing labels that we know we have. So going through this process, we're able to refine the parameters within the unit iteratively and generate a pretty decently accurate model.
Cool, thank you.
So what are the fundamental differences between the process that you're working on and the existing, I guess, artificial intelligence ones that you were talking about?
Sure. So I guess specifically you're talking about these benchmarks.
Yes.
There. Okay. So both of these models are what we call auto-ML, so auto machine learning. So what these do is they leverage data analysis to generate algorithms. So they'll look at the entire data set and generate all of these good parameters that they think are the best ones. Now, while our pipeline isn't necessarily an auto-ML pipeline, it has just the deep learning aspect. So we're trying to generate an idea of where we fall within these auto-ML pipelines, which will likely be better than ours. But we want to know from scratch, can we actually generate something that's able to compete with this?
That's really cool. So you said it took about 1 to 3 hours to generate that image where you being able to identify the organs. Would a hospital be able to do that in house, or would you need access to a supercomputer
Sure.
to do this?
So the training, of course, is done on a high-performance computer. So the training, it does require quite a bit of infrastructure. However, the actual inference doesn't take that long. Actually, it only takes about 1 minute to generate a segmentation, a 3D segmentation of a full CT image. Now, the reason we say it takes 1 to 3 hours is because we have to pass that segmentation along through a series of medical physicists, radiation oncologists, who vet that image, will go through, make small edits, will discuss with their peers, and that process usually takes 1 to 3 weeks because there's so much more manpower involved in making those drawings up from scratch. So as far as inference go, it can be done right at the point of care, and it can be done fairly